Hello everyone. In this video, we'll discuss about the slip and the effect of slip on the rotor parameters. We all know that the induction motor works on the principle of mutual induction. So here a three-phase AC supply is given to the stator. As a result, a rotating magnetic field will be produced. So the speed of the rotating magnetic field is given by the synchronous speed, which is nothing but 120 F by P, where F is the frequency of the supply voltage and P is the number of poles of the stator. Okay, so now the rotor will start rotating at a speed slightly lesser than the synchronous speed. So the speed of the rotor under steady state condition will always be lesser than the synchronous speed. So the difference in this speed, ns minus n, is defined as the slip speed. Okay, so now we'll define a term called slip. So the slip is nothing but the slip speed expressed as a fraction of the synchronous speed. Okay, so slip is defined as the slip speed expressed as a fraction of synchronous speed ns. So the slip is given by S is equal to ns minus n divided by ns. Or if we want to express it in percentage, so percentage S is equal to ns minus n divided by ns into 100. So now if we cross multiply, we'll get S into ns is equal to ns minus n. On rearranging this equation, we can write n is equal to ns minus s into ns. So taking ns outside, this will be 1 minus s. So the rotor speed in terms of slip is given by n is equal to ns into 1 minus s. So when the rotor is not rotating, that is at standstill, n is equal to 0. In that case, the slip is given by 1 minus s is equal to 0 or s is equal to 1. So when the speed of the rotor is 0, slip is equal to 1. So this is the maximum value of the speed that can be obtained in the induction motor. Now we'll discuss the effect of slip on the rotor parameters. Initially, when the rotor is not rotating, in that case EMF will be induced in the rotor. So this EMF depends on the synchronous speed. Okay, so the frequency of the induced EMF depends on the supply frequency F. Okay, so this E2 will depend on the supply frequency F. But as and when the rotor starts rotating, this frequency will no longer be equal to the supply frequency. In that case, the rotor frequency or the EMF of the rotor frequency will be equal to some other frequency, say Fr. So this is due to the fact that this induced EMF will depend on the slip speed. Okay, due to this slip speed, the frequency also varies. Okay, due to the presence of the slip on the induction motor, the frequency will vary. Okay, so now we all know that the synchronous speed can be written as ns is equal to 120 F by P. Let this be equation 1. Now, as the speed varies, ns minus n can be written as 120 Fr by P, where P is the number of poles of the rotor. Okay, so the number of poles of the stator and the rotor will be equal. So this is equation number 2. So if we divide this equation 2 by 1, we will get ns minus n by ns is equal to 120 Fr by P divided by 120 F by P. So this 120 F by P will get cancelled. The remaining terms will be Fr by F. On the left hand side, we will have S is equal to Fr by F, or this can be written as Fr is equal to S times Fr. So this is equation number 3. Now the frequency of the EMF induced in the rotor under rotating condition will be equal to S times the frequency of the supply voltage. Okay, so this is effect of slip on the frequency. So next we'll discuss the effect of slip on rotor EMF. Okay, so as we have already discussed, under standstill condition E2 is proportional to ns. Under rotating condition, E2R is proportional to ns minus n. So if we divide these two, we'll get E2R by E2 is equal to Ns minus N divided by Ns. So this is again E2R is equal to S times E2. Okay. So the EMF induced in the rotor under rotating condition will be equal to S times the EMF induced in the rotor under standstill condition. So now we'll see the effect of slip. Effect of slip on rotor impedance. So in a similar fashion, the impedance of the rotor also varies. So now suppose R2 is the resistance of the rotor. Okay. So this is the resistance of rotor and X2 is the reactance of the rotor under standstill condition. Okay, standstill means when the rotor is not rotating. Okay, so this X2 is given by 2 pi F into L2. Okay, so this X2 under standstill condition depends on the frequency of the supply voltage. When the rotor starts rotating, this X2 will no longer depend on F, but it depends on Fr. Okay, so this expression will become 2 pi Fr into L2. So where X2R is the rotor reactance under rotating condition. Okay, this is the reactance of the rotor under running condition. So when the rotor starts rotating, due to the effect of the slip, the frequency changes. As a result, the reactance also changes. So if we divide these two equations, again we will get an expression. X2R by X2 will be equal to 2 pi Fr into L2 divided by 2 pi F into L2. So 2 pi L2 will get cancelled. So this Fr can be written as S times F. So divided by F, FF will get cancelled. So again this X2R can be written as S into X2. Okay, this is the reactance of the rotor under running condition. So now Z2, which is the impedance, is given by R2 plus JX2. This is during standstill, that is when the rotor is not rotating. So now when the rotor is rotating, R2 will remain the same.
R2 is independent of the slip.
But X2 will become J into S into X2. So this is the impedance of the rotor under running condition. Next we'll see the effect of slip on the rotor current. So now the rotor current I2 will be equal to E2 by Z2 under standstill condition, that is when the rotor is not rotating. So whenever the rotor starts rotating, I2 will become I2R. This depends on E2R divided by Z2R. So E2R already we have derived S into E2, and similarly Z2R we all know R2 plus J into S into X2. So now this is I2R, this is the current flowing through the rotor under running condition. Okay. So due to the presence of slip, the current also changes, magnitude of the current. So next we'll see the effect of slip on the power factor. Okay, suppose cos phi 2 is the power factor of the rotor. So cos phi 2 is the power factor of the rotor under standstill condition. So power factor is given by R2 divided by Z2. So R2 divided by R2 plus J into J into X2. Okay, this is during standstill condition. So again, when the rotor is rotating, due to the effect of this slip, cos phi 2R will become R2 divided by Z2R. So this will be equal to R2 divided by R2 square root of R2 square plus Sx2 whole square. Now we'll solve a small numerical. Three-phase 50 Hz induction motor has two poles. If the slip is 2% at certain load, determine the speed of the motor. So first we'll write the given data. So frequency is given. Frequency F is equal to 50 Hz and the motor has two poles. So P is equal to 2 and the slip is 2%, 2 by 100, or this is equal to 0.02. Okay. So now we have to find out the speed, actual speed of the motor. So we know that actual speed of the motor is equal to 1 minus S into Ns, where Ns is a synchronous speed. So for ns, the formula is 120 F divided by P. So 120 into 50 divided by 2. So this will give you 3000 RPM. Okay. So now we'll substitute in this formula n. N is equal to 1 minus 0.02 multiplied by 3000. So this will be equal to 0.98 into 3000. That is equal to 2940 RPM. So next to second problem. Here a 3-phase 4-pole 50 Hz induction motor is running at 1440 RPM. Determine the slip speed and slip. So first we will write the given data. So number of poles P is equal to 4. Frequency F is equal to 50 Hz. And actual speed of the motor N is equal to 1440 RPM. So we have to find out slip as well as slip speed. So ns minus n. Okay. So first we will find out the synchronous speed. Ns is equal to 120 F by P. So 120 into 50 divided by 4. Okay. So this will be equal to 1500 RPM. Okay. So next we will find out the slip speed. Slip speed is equal to ns minus n. So 1500 minus 1440. This will be equal to 60 RPM. So next we will find out the slip value. So slip S is equal to ns minus n divided by ns. So 60 divided by 1500. So this will be equal to 0.04. So if you want to express it in percentage, this will be equal to 0.04 into 100 or 4%.